In this video, I'll be showing you guys how to use the ratio test to determine whether or not a series converges or diverges. So let's go ahead and set up the format right here. So we have a series that goes on to infinity for the sequence a of n. What is the ratio test? Well, the ratio test gives you some value of r, correct? And this value of r is determined by the limit as n approaches infinity for a of n plus 1 over a of n. So what is a of n plus 1? Well, a of n plus 1 is simply the next term in your sequence a of n. So let's say you had some sequence 1, 2, 3, right? If this was a of n, this is your second term, n is equal to 2 in this case, then your next term would simply be a of n plus 1. So a of n plus 1 just represents the next number inside of your sequence. Well, here's the thing about the ratio test. I'm going to state the conditions. If r... set up all the r's. If r is less than 1, then your series converges. If r is greater than 1, your series diverges. And if r is equal to 1, your series is inconclusive. Well, here's the thing about this little problem. Okay, we want to know a ratio. Right? That's the name of the test. It's a ratio test. Well, how do you use this? Okay. Well, normally you're going to be using this for exponential and factorials. So if you see like a factorial n to the power of 1, n factorial, right? 2n factorial, your problem. 2n plus 3 factorial, or something like that. Or like even like n to the power of n, or 5 to the power of n. You're going to use ratio test most likely in those problems, in those series, okay? So that I guess you'll just know when or not to use ratio test based off of those little things, exponentials and factorials. But let's get back into the conditions. I'm going to explain the logic of the conditions. If you don't really care to understand the logic of the conditions, you can just skip this part and go on to the problems. But in the case when r is less than 1, that means that the ratio between the sequence's next number and the previous number is decreasing. Right, so let's go ahead and use the example 1, 2, and 3. Okay, If this was a of n, and this is a of n plus 1, we put a of n plus 1 over a of n, what do we get? We get 3 over 2. Well, that means a of n plus 1 is greater than a of n. So the next number in your sequence is greater than the previous number. And if that is the case, then that means your series is increasing. And the reason why we take the limit as n approaches infinity is because we want to understand the behavior of the function as it approaches infinity. Right? We don't care about really the beginning of the sequences, right? Maybe sometimes a of n plus 1 is going to be less than a of n until it reaches a certain point, and then a of n plus 1 increases way faster than a of n. All right? But we want to determine this behavior as n approaches infinity since we're taking an infinite series. But basically what we're doing is we're testing the ratio between the next number and the previous number. And if the ratio of the next number is greater, if the next number is greater than the previous number, then the ratio between them will be greater than 1, correct? And that means the series increases as you approach infinity. So if the series is increasing as you approach infinity, doesn't that mean that you'll never converge? Right? If you add 1 plus 2 plus 3 plus 4 plus 5, constantly, increasing function, increasing series, then you're eventually gonna hit infinity if you keep adding them up to infinity, the sequence up to infinity. But what if the ratio between the numbers is actually less than 1, right? So let's use the example 1/4, 1/16, and actually let's use 1/3, 1/3, 1/9. I wrote a G there. Wow, 1/9, 1/27, Okay, let's call this a of n. Let's call this a of n plus 1. Well, a of n plus 1 is the next number, correct? Well, if you take the ratio between these two, you get 1 over 27, which is a of n plus 1, over a of n, right? That's the previous number, 1 over 9. We get 1/3 if we do this. Well, that means that the next number, as you approach infinity, will be less than the previous number. And if the next number in your sequence is constantly getting smaller and smaller and smaller, if you go on to infinity, it can't really get any smaller, correct? If it just keeps getting smaller and smaller and smaller, you're going to hit 0. And eventually, you're not gonna the value of the series isn't going to increase or decrease anymore. It's simply going to converge at a value. So that's why the ratio test works, but r is equal to 1 is just inconclusive. An example of a series that's inconclusive using the ratio test is simply 1 over n, right? If you wanted to try that, of course. But let's go ahead and do some problems, because that's really where you actually learn how to use this stuff. Let's go ahead and use ratio test on this, and the reason why is because we see an exponential, right? 5 to the power of n is an exponential. So how do you find r? Remember, r is found as the limit approaches, the limit of n approaches infinity for a of n plus 1 over a of n. So what's a of n in this case? Well, a of n is simply this guy right here, the original series. So let's go ahead and set up this guy. Let's actually ignore the limit for now so we have less writing. But set the limit, we get 5 n plus 1 over n plus 1 to the power of 4 over a of n. A of n is simply the original series, 5 to the power n over n to the power of 4. This guy can be simplified further to get 5n to the power of 1. What am I saying? 5 to the power of n plus 1 over n plus 1 to the power of 4 times the reciprocal of the denominator, which is simply n to the power of 4 over 5n. Well, here's where the pre-calculus comes in. Yes, pre-calculus comes into here. We can separate this exponent, 5 to the power of n, to look like this. Remember, if you multiply exponents with the same bases, then you can add the exponents together. If you add exponential functions with the same bases, you can add the exponents together. And what we did here, 5 is the same base here. And since they have the same bases, we can simply just add their exponents n and 1 to get n plus 1. And we put this over n plus 1 to the power of 4 times n to the power of 4 over 5n. Here's the thing about this. These n to the power of 5s cancel out. And we actually get left off with 5n to the power of 4 over n plus 1 to the power of 4. Now remember, we have to take the limit of this guy. Let's go ahead and take this limit. So if we take the limit, n approaches infinity, of this function, we should only worry about the highest exponents in the numerator and denominator, correct? When you're taking limits to infinity, you only worry about the highest exponents in the numerator and denominator. So simply this becomes the limit as n approaches infinity for 5n to the power 4 over n to the power 4. Right? N to the power 4 is your highest exponent if you expand this guy right here. Well, what does this become? Well, this simply becomes 5 because the n to the power 4 just cancel out in the numerator and denominator. Here's the thing about this. 5 is equal to r, correct? Well, remember our conditions for the ratio test. If r is greater than 1, then your series diverges. Remember, the ratio of the next number is greater than the ratio of the previous number. Wait. What am I saying? The next number is greater than the previous number, therefore the ratio between them is greater than 1. So, if that's the case, then that means this series diverges since the r value we got was greater than 1. Actually, I can just point the arrow from the already written diverges. Well, one thing you'll learn as you do ratio tests is that factorials grow faster than exponential functions, and exponential functions grow faster than power functions. So in the previous problem, we had 5 to the power of n over n to the power of 4. Well, exponential, this guy's exponential since n is raised to the power, and this guy's a power function. And usually exponential functions grow faster. And since this guy grew faster, that's why that previous series diverged. But in this case, we have a factorial. And you will also learn that factorials grow faster than exponentials. So what we have here, I guess you can already conclude that it converges, but let's go ahead and actually prove that using the ratio test. Let's go ahead and find r. And let's take the limit, wrong color, limit as n approaches infinity for a of n plus 1 over a of n. So what's a of n plus 1? Do not do that. What is a of n plus 1? A of n plus 1 is 3n plus 1 over n plus 1 factorial. Over a of n, which is 3n over n factorial. Well, what you can do here is simply multiply by the reciprocal of the denominator. Get n plus 1 factorial. Let's make some more space. for this guy. So you get n plus 1 factorial times n factorial over 3 to the power of n. Well, what you can also do is decompose this exponent to get 3n times 3 to the power of 1 over n plus 1 times n factorial. Now, if you're confused on why this works and why you can separate this factorial in this way, then I'll do a quick explanation for you, because I know, like a lot of pre-calculus classes and calculus classes, I've never covered this, and you just need to work it out with logic. So let's go ahead and help you with that logic. So n factorial is equal to, right, each previous number of n, so n times n minus 1, right, times n minus 2, correct? So if there was, let's say, 4 factorial, then it would be 4 times 3 times 2 times 1. Every single previous number behind 4, you just multiply it all together. Well, let's consider the function n plus 1 factorial in this case. Well, if n plus 1 factorial is equal to 4 factorial, then n in this case would simply be equal to 3, correct? If n is equal to 3, then you get 3 plus 1, which is equal to 4. And then 4 factorial is equal to 4 factorial, right? Well, if n is equal to 3, why does this equal this? Let's go ahead and keep this in our head. N is equal to 3, okay? If n is equal to 3, then n factorial, right? Or also 3 factorial is equal to 3 times 2 times 1. Correct? And 3 times 2 times 1 is the beginning, the right side of this expansion. Right? It's the beginning terms 1, 2, and 3. Now what's n plus 1? Well, n plus 1 is equal to n factorial. N plus 1 is equal to 4. And if we multiply 4 times 3 factorial, we get 4 factorial. All right? 4, if we multiply n plus 1 times n factorial in this case, for the example n is equal to 3, then we get 4, since 4 is equal to n plus 1, 4 times n factorial. And n factorial was equal to 3 factorial, which is 3 times 2 times 1. And due to that logic, n plus 1 factorial is equal to n plus 1 times n factorial. Now, this was a little confusing for me to grasp at the beginning, so I don't blame you if you don't get that. But really get comfortable with these, because you're going to get something eventually. Hopefully you don't get this, but likely you will. You're going to get something that looks like this. How in the world do you decompose this? Right. Well, I'll cover a problem like that as well in this video, but let's go on with this problem. So you have n factorial over 3 to the power of n, correct? That's the this part of the function. You can actually cancel out 3 to the power of n, and now you can actually cancel n factorials here. So you can get rid of the factorials now. That's why you wanted to take the n factorial out. So you can get 3 over n plus 1 in this case. Well, remember, this is a limit. So if we take the limit as n approaches infinity for 3 over n plus 1, we get 0. So 0 is equal to r. And the condition for r, when r is less than 1, is that the series converges. So if r is less than 1, your series converges. Therefore, this guy right here, 3 to the power of n over n factorial, converges. And again, I already hinted at this. Your factorials grow so much faster than your exponentials that as you approach infinity, your factorial is just basically sending this guy straight into nothingness. n to the 3 to the power of n is going into straight nothingness, which is why, since the denominator grows faster than the numerator in this fraction, you're going to get smaller and smaller numbers in your sequence, which result in you eventually converging at some point or at some value. So we have this really ugly factorial, just like you guys. Just kidding. Maybe not. But this very ugly factorial, we can simplify in a way that was very similar to the previous factorial. So remember, we want to find r by taking the limit as n approaches infinity for a of n plus 1 over a of n. Right? Let's go ahead and write that down. So a of n plus 1 is equal to 8 to the power of n plus 1 over 2 times n plus 1 plus 3 factorial times the reciprocal of a of n. All right, we've done this enough, so I hope you know why I'm multiplying by the reciprocal over 8 to the power of n. What we can do is separate this more, right? This exponential can be separated into 8 to the power of n over, 8 to the power of n times 8 to the power of 1 over 2n plus 5. I simply distributed the 2 into this n plus 1 term. So we get 2n plus 5 factorial times 2n plus 3 factorial over 8n. Now here's the thing about this 2n plus 5 factorial. We can actually simplify this. We can set this equal to 2n plus 5 times 2n plus 4 times 2n plus 3 factorial. Well, why can we do this? Well, first off, the reason why we want to do this is so we can actually cancel out this 2n plus 3 factorial terms. We get, since this is going to be in the denominator and this is going to be in the numerator, they're actually going to cancel out at the end. But why can we do this? Let's go ahead and use the example where n is equal to 1. Well, when n is equal to 1, this term is equal to 7 factorial, correct? Well, 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. Very big number. All right, well, what do we have next? Well, we have this right here. Remember, we said n is equal to 1. Well, when n is equal to 1, let's go ahead and only worry about this guy first. When n is equal to 1, we simply have 5 factorial here, correct? This is when n is equal to 1. So 5 factorial for this term is equal to 5 times 4 times 3 times 2 times 1. All right? Well, here's the thing about this. What about these guys? Well, when n is equal to 1, you have a 7 here. When n is also equal to 1, you have a 6 here. So if you have a 6, 7, wait, 6, 7. Okay, I'm probably, if I'm saying that right now and you're watching this 2 years later, I probably sound corny as hell, okay? But 6, 7 is just a meme currently, right? That people are just saying on the internet to rage bait or some shit. But, all right, we have a 6 and a 7. Well, if we multiply the 6 and 7 by the 5 factorial we previously had, we have 6 times 7. Look at here. We actually have the original factorial, 7 factorial. Right? So these sides are actually equal. The reason why this works is because these guys that we took out, right, are simply the extra parts of the factorial that we multiply by. So if we decrease the added constant, plus 5, by 2, right? So we decrease plus 5 by 2 to get plus 3 and still leave the factorial. We need to take into account the next two numbers that we multiply by in your factorial. And those next two numbers can simply be taken into account by using plus 4 and plus 5, right? We just increment up by 1 and then multiply that factorial, like so. So that's why this works. Now, if that's a little confusing, trust me, I understand better than anyone else because... Well, I understand maybe this is probably the same as you guys because, geez, man. I did not expect a factorial manipulation. I didn't expect factorial manipulation in my Calculus 2 class. But basically what happens right here, 8 to the power of n actually cancels out. So we get 8 over your newly expanded factorial, which is this right here. I'm just going to copy and paste this so I don't have to rewrite it, which is right here. Times, since this is canceled out, we just simply leave out the numerator to get 2n plus 3 factorial. And this 2n plus 3 factorial is canceled out, so we get left off with our limit function. Remember, we have to take a limit. So the limit as n approaches infinity for 8 over 2n plus 5 times 2n plus 4. This is simply equal to the limit as n approaches infinity for 8 over, remember we only care about the largest exponents when we're taking limits to infinity, so 8 over 4n squared. So if you were to use FOIL to expand these two guys, you would get that the largest exponents of 4n squared. That's simply just for multiplying 2n times 2n here. So now we have this. Well, as the limit as n approaches infinity, n is only approaching infinity in the denominator. So basically what you're getting is 8 over infinity, which is just 0. Right? So this limit actually approaches infinity. And remember, 0 is equal to r. And since r is less than 1, your series converges. Therefore, this guy right here converges. So I really hope that this video helped. Yes, ratio test, a lot of talking. I've made so many videos lately, and I've been singing while playing the piano, so my throat is like tired. Yeah, but I think that maybe I'll make like 1 more video, 2 more videos today, 3 more videos today. But as always, if you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.